Yes, so my name's Karin Reinke. I've been working with Simon, Shamel and a number of other researchers into this space in using Himawari-8 for early fire detection. And we're now approaching sort of, I guess, the end point or the pointy end of the project where we're able to start delivering hotspots in an operational context. That's probably the good point to hand over to Shamel and allow Shamel to introduce herself.
Hi, Karen. So I'm going to introduce myself a bit more thoroughly as we go through the presentation. But for the moment, I'm a postdoc working at RMIT, trying my best to detect Himawari-8 hotspots using an algorithm that we developed with me, Simon, and Corinne that has shown promise so far from our early results.
So Naomi Withers, I'm from DELP and I manage EMAP, which is the operational fire response system for Victoria. And we've operationalised using the Himawari-8 hotspots, which RMIT is developing, into our response system, mapping system for the current fire season. And I'll just be presenting some of the information and results that we got from this season.
Thanks. Yeah, Stuart Matthews from the Fire Service. I'm a fire behaviour analyst and also look after some of our systems there. And yeah, we've been working with Shamel and the team on testing the hotspots product and looking at it in some of our operational systems over the last couple of seasons.
And I'll just make an apology for Simon Jones, who at last minute couldn't make it today. So just add that apology.
Thank you. So what I'll start with is actually an image that I got from DELP from Stephen Sleafield. He sent it to us shortly after we officially started delivering hotspots to Victoria. And this is an example of the use of Himawari-8 hotspots in an operational sense, which might be familiar to you. To give you an idea of how the hotspots work, I'll go through this sort of movie, which shows some of the Himawari-8 hotspots that were coming out of our multivariate spatio-temporally adaptive threshold system in real time. And we were delivering them to New South Wales. We covered New South Wales and Victoria. Each magenta point shows a detection that was delivered to New South Wales Real Fire Service within 2 minutes of the data arriving in our hands. On the left, you see visible satellite imagery, and on the right, you see middle infrared satellite imagery. And at the moment, we're in the 29th of December, 2019. You can see lots of cloud coming over the scene, but even with the cloud, there are intermittent detections from the MSAT Himawari-8 system. And as we're cycling through day and night, the fires intensify, and it's just a beautiful set of imagery to look at how having high frequency satellite information can be useful for looking at fire behavior and getting information about where fires are, whether they're increasing or diminishing. I'll let the movie finish because it's quite close to the end. Oh, sorry, I accidentally just restarted it. But what I wanted to say is this whole system that we've built, we've been delivering hotspots to Stuart Matthews' team at New South Wales Rural Fire Service since about 15th of March 2019. All of these hotspots and their delivery was done without any access to high performance computing. We used a fairly average computer to do the processing that we've done. So the early results are quite promising. The fact that we've been able to do them with the resources that we have is really encouraging. So when we move from the system that we have already created with the resources we have to a high performance computing environment, the possibility of us delivering hotspots to the whole entire Australian region in very short times, possibly far less than the 2-minute delivery time, is a really strong possibility. And that's exciting. So I guess you might look at a movie like that, and I'm sure some of you see issues, but some of you think it's really exciting, and you might want to look at it and go, wow, so it was easy, right? And problem solved, let's just put it into operations, it's all done. And I just want to emphasize, the main point I want to drive home through the presentation is that, no, it wasn't easy, and it's actually a really complex problem to try and reliably get hotspot detections from data like the Himawari-8 satellite data with a minimum amount of errors, and beyond just being able to solve the problem. The thing to remember with the development of this system is just how complex the data handling and pushing around of everything and getting things out in as close to real time as possible. There's a lot of engineering behind that. And although we've made huge strides and a lot of progress in what I feel is quite a short period of time, we got that far because Simon Jones, Corinne Weinke and I, we have a lot of collective experience, and we put every little bit, scrap of everything we knew into the bucket to try and get this problem solved as quickly as possible. We've come far, there's more to go, but hopefully we've achieved something. And just to give you an idea, because most of you would never have met me, is I work at RMIT in geospatial science, but I actually have a background in real-time statistical post-processing to get decision-making information out to weather forecasters using all local and international weather forecasting information in real time. I've got that in my pocket. I worked on data and simulation. And before I came to RMIT, I was actually working on modeling of the weather and the fire behavior on the day of Black Saturday. And so from all the experience that, for me personally, all the experience that I had before I came to this project gave me a slightly different viewpoint where I understood the importance of a minute and the timeliness of the data arriving in researchers, well, in fire behavior analysts' hands. That it's not just about solving the problem, it's about solving it as quickly and accurately as you can. Let's just step back a little bit and think about the problem as a whole. So we think about the problem with finding data to help support fire behavior analysts for fires, that there's actually quite a few different layers of that problem. One is that you want to detect the fires, you want to track the fires, you want to record the fires, but some of this can be done way offline. You might be looking at it months after the fact, and it doesn't matter to you whether or not you're getting the data in real time. But for other instances, if you can get the data super quickly, you might be able to change the outcome of the fire. You might be able to help the fire to be put out. So it's actually a very complex problem within itself of what's trying to be solved. And the thing about fire in particular as a problem space is that fires rapidly change, as we all know. So the frequency of information becomes crucially important, and when the information becomes available is crucially important. So for you as a community of fire behavior analysts, I know that you have many different tools available. You have LiDARs that fly on planes, you've got people that can tell you what's happening in the field in terms of fire. But one of the tools that you do have available is fire information that comes from Earth observation satellites. And essentially what is an Earth observation satellite? It's a camera that's moving around outside of the atmosphere of the Earth, rotating around the Earth, taking pictures. And we can use those pictures to tell us things about what's happening down on the Earth. The most familiar kind of imagery that you may have come across is something like what you can see here from the NASA Worldview website. This is a Modus AFAC image from the 1st of January 2020. It's a true color image, and the little red specks that you can see on that image are the fire and thermal anomalies that were detected by the Modus system, automated detections without any human intervention at all. Modus produces really beautiful imagery, and like just every time I look at an image like that, I really think about how far we've come, and just the amount of information that we have available to us. But there are other sources of information that also will be additionally useful as well. So if you think of MODIS, I'm not sure if you can see my pointer here, but if you think of MODIS, it's a low Earth orbit satellite, and it travels around the Earth in like a constant circle in a ribbon while the Earth spins, and it just goes round and around at about 705 kilometers above the Earth. So it's not constantly viewing the same spot. It's going to change the spot that it's looking at, which means that it might see it in really high resolution, but it's going to have to wait for the Earth to spin before it will return to the same spot again. So one physical low Earth orbit, well, for MODIS, with its orbit, it will pass over the same point in the Earth 2 times a day, once during the sun, during the day when the sunlight, and once at night. In comparison, there's another type of satellite available, which is the geostationary Earth orbit satellites. And on this plot, which I took from the Japan Meteorological Agency website, it shows you the history of the geostationary Earth satellites. But I hope you can see my pointer. But the green line here shows the position of the Himawari-8 satellite. And the Himawari-8 satellite actually moves as the Earth turns. It moves in sync with the Earth. So it's always looking at the same point of the Earth. And what you get out, the difference between what you get out of something like MODIS, which is on the left, which is a polar orbiting satellite, and something like the Himawari-8 satellite, which is geostationary on the right, is that geostationary sees one full disk, constant full disk image, and it just keeps on scanning that image, continually returning this scan of that image every 10 minutes. So you get high frequency observations from the geostationary satellite, whereas for the polar orbiting, it is moving constantly. It's constantly taking images, but they're not over the same spot.
Jamal, sorry to jump across you there.
Yeah,
just a question, because something that came up that I thought was quite interesting is when you were looking at those low Earth orbit satellites, such as MODIS, you saw that basically as it moved across the continent, as it moved from the east across to the west, there was basically a blind spot throughout a diurnal cycle where we weren't seeing the landscape, and that seemed to occur kind of or coincide with that afternoon period where often you'll get that wind shift and see a change in that fire front and that behaviour that fire activity. So, you know, it was almost happening. We were losing sight from our the low Earth orbit satellites at a time where it was almost most critical as it was shifting across the continent. So I think that just as a point, I think that was that's something that's quite important.
Oh, you're absolutely correct, and it's going to come up again later in the presentation when we're comparing our hotspots to the MODIS hotspots. But if you look at just a picture of Earth on the geostationary satellite here, the thing about the polar orbiting is we don't get to choose what time it crosses. It just crosses when it crosses. That's the orbit for the entire globe. And on the east coast of Australia, the latest daylight observation tends to happen at about, so like on the east coast, it roughly passes on about 4 UTC, which is about 2 o'clock in the afternoon, whereas to the west coast, I think it's about 6, I hope. I haven't looked at the times recently, but which means that it's extremely useful information. And we're not trying to say that this information is not useful. It's just that it's not necessarily optimal for the purpose of detecting fires over Australia. Okay, so hopefully you can see from what I've told you that there's a reason why geostationary satellite data is particularly exciting for an application such as trying to detect fires. And one of the reasons that it's so exciting is because of the high temporal resolution. You've got a new observation arriving every 10 minutes, but with that sort of real opportunity that you have in that data, there is an important distinction given that the trade-off that you get from using a geostationary satellite, it sits at about 35,800 kilometers away from the Earth. And it's incredible that you can get detail down to a resolution of about 2 kilometer by 2 kilometer pixel size in the 3 micrometer band. It's amazing that we can get that level of detail. But But given that it sits so far from the Earth, it doesn't match the level of detail that you get from a low Earth orbiting satellite like MODIS, traveling about 705 kilometers from the Earth. It gets more detail in its observation. And it's that difference in the level of detail that we really have to be careful with when we're trying to develop algorithms. And there's one other thing that for Himawari-8 in particular, and I'm sure there's people here who might have access to different sets of information that I do. But when you, as a researcher, when you go away and look at the Himawari-8 satellite data, it does not arrive with an accompanying cloud mask. And to show you what a cloud mask actually is and why it's important for being able to detect fires, on the left, you can see a true color image from the Himawari-8 satellite. I made this, and on the right is a 3.9 micrometer, that's a mid-infrared image. And magenta is just a mask that I applied for a cloud mask that we derived for another project. And when you have cloud mask information available, you can use that to take clouds out of the data set prior to starting to look for fires. And hopefully I can explain why that's important a bit later. But the problem with cloud masks in particular is that they differ in quality. Like creating a cloud mask in itself is a major exercise, and they're not always actually accurate, even for well-established data sets. And the other thing is that they take time to produce. So we had an option to either create our own cloud mask and then look for fires and take up precious minutes and time doing that, or to just try and find a way to be able to process the Himawari-8 satellite data without a cloud mask, because our aim in doing this research was to get as accurate as possible fire information into the hands of fire behavior analysts as soon as possible, understanding that every minute counts and that it doesn't matter necessarily if we can get the weakest detection of a fire and we can hand it to you in 3 hours time after the fact. We understand that that might be useful for historical reporting of fires or recording how the fires actually progress. In terms of being able to change the outcome, it's far more important to have an algorithm that works as fast as possible while being as accurate as possible to get the information to the right people at the right time. So just to summarize before I move on to what we actually did, the problem in our eyes is that we're trying to detect fires, but we're trying to detect it in the shortest amount of time from the minute that the data arrives in our hands. We've got lots of data and it's arriving every 10 minutes. We know that the spatial detail is something that we have to work with, and we have no information a priori about things like weather information such as clouds. So next I'm going to dive in a little bit into what we actually did to be able to get the information out to the New South Wales Rural Fire Service and later to the Victorian Rural Fire Service, which was really, really exciting for us to know that our researchers were used to people in the world. So in order to solve this problem in the way that we felt was most appropriate, we developed an algorithm that we've called a multivariate spatio-temporally adaptive thresholds system, and we've applied it to detect active fires. So I'll apologize for people if you've seen this before, but I'm just covering a bit of ground for anybody who is not super familiar with this space. If you look at data coming from the 3.micron mid-infrared satellite channel from any satellite, what you'll find is that a fire, even if it only takes up a fraction of the area that the pixel of the satellite actually represents, can produce enough radiant energy that it can actually raise the brightness temperature in that channel. So I've got my plus sign here, but the problem is you can't depend on that alone because other things can do that too. And clouds can also raise the mid-infrared satellite values, but clouds can also lower them as well. So clouds complicate the ability to detect fires greatly, and we can't depend on one channel alone. And the other issue is, we know that arrays in the mid-infrared, or the 3.9 micrometer value, is most likely going to indicate a fire, but raised against what? There's no consistently available value for any place in the world because it changes with season, the time of day, and it also changes with where you are. So when you're trying to decide if, let's pretend the central pixel, we're trying to decide, is it raised compared to every other pixel here? In this case, it's probably easy if you've got clear data. Here, next one, I've got gray ones where if you could accurately mask out the cloud, you could still be able to do it. But what happens when your radius becomes really small? It becomes a bit harder to decide, is that radius due to a fire or is it something else? But the problem starts to lie when you have stuff around you that you can't be sure of. You might have clouds that are around you, and if you include that data, it might actually raise the background or it might lower the background because of how reflected sunlight affects that channel. And underlying that as well is that you have significant differences in the landscape and the response of the landscape in that channel. So it can be difficult to decide, like to compare your data and do your relative comparisons. Anyway, to get around this, what the traditional fire detection algorithms, what we do as well, is we use multiple satellite channels. We use the mid-infrared, which is represented in our data set by the 3.9 micrometer channel. We use the thermal infrared data, which is 10.4 micrometer. We use that to decide whether it is a fire and also decide whether or not that may be a cloudy data point. And we also use visible information from the 0.64 micrometer channel, but that's only really useful in the daytime. It's only available in the daytime. So what we did in our algorithm was we looked at the data set that was coming from the Himawari-8 satellite. And what we realized is that because it's a geostationary satellite data set, we consistently have data available every 10 minutes over Australia over a really long, consistent time frame. So we've got years of data available consistently, whereas it's different compared to MODIS, where you've got the wrapping around of the MODIS. You're not guaranteed that it's going to return to the exact same spot on a given day. So you can't really, you've got different opportunities in each of the data sets. So in a geostationary data set, you have an opportunity to do your detections based solely on the data alone. And what we did was we produced a data-driven threshold algorithm where we look at the data over multiple times, historical times and recent times, well, over a 4-week window in this case. And we allow them to vary. We don't take a threshold over all of Australia because we know that all of Australia is vast and it has different characteristics. We've got tropical parts in Australia. We've got our alpine regions in Australia, coastal, we've got deserts in Australia. You can't expect one set of thresholds to be optimal for the whole of Australia. Instead, what we did was we used our understanding of the actual physical problem and looked at the underlying landscape differences and differences in the biology and the geographic characterization of Australia. And we broke up the data set into regions. And then again, we broke them up and allowed the thresholds to vary with region, with season and the diurnal cycle. And that was in our regional work, which was like a historical way of looking at hotspots. We did that. And then after that historical kind of view of hotspots, we transformed the system to work in real time. So we've got a running 4-week window, which just keeps on doing the similar things. And just to give you, drive home the fact why it's important that the thresholds are not calculated for all of Australia and rather they're calculated for regions and seasons. This is one time point, I think it's at 4 UTC. This is a thermal infrared channel, and these are thresholds that were calculated for all of Australia in early summer on the left and early winter on the right. And you just want to notice that there's spatial variation in both images, but when you compare the two images, there's also a lot of variation as well. So if I had a training data set in the middle of summer and I found out the best possible threshold that could, be applied to somewhere like Darwin, I wouldn't want to take that threshold and apply it through the whole entire year because seasons change, things change. And with geostationary satellite data, we have the data available to be able to be more adaptive in space and in time. And so in order to calculate hotspots, this is sort of a rough image of how we began with our hotspot detection algorithm. We take full data sets. This is just one region over multiple days. We use all the information at the same time from the multiple channels, being 3.9, 10.4, and 0.6 for micrometer data. We look at the data separately and all together as a whole, so we can get statistically significant data. And what we're asking ourselves when we look at all that data together in one go is, do we have enough information? Is it statistically reliable information, or do we think it's been too affected by cloud? If we have enough reliable information, we go ahead and we do a data-driven method where we calculate thresholds which we think most accurately represent that specific region on that day at that time of day. And if we don't have enough data to create that information reliably, then we switch around and we just use a simpler method to go, well, we don't have enough data to detect the hotspots using a really complex method today, but let's not completely give up. We'll still try and push out hotspots if they're really super strong. So we've run the New South Wales and Victoria trials, so that started on the, we started in February, but with a bit of consultation with Stuart Matthews, we actually updated our algorithm, and really, we had some ideas and we just laid them all out on the table, and we put that into the algorithm and we just started pushing out hotspots. And we were receiving them at the same time as New South Wales River Fire Service was receiving them. And we looked to see how the algorithm developed and how it performed. And that was really our first cut at a real-time algorithm for Himawari-8 satellite detection. And now what we're doing is going back and comparing it to other satellites to sort of say with scientific divinity whether or not the algorithm is working as well as we would want it to. But it's a complex issue, and I'll go through it more as we go. Here's an example of the whole of Australia. On the trial, we only did New South Wales and Victoria to begin with, because we'd never done it before. It was something new. We tried it on a small region. But I've gone back and recalculated a couple of days over the whole of Australia using the real-time algorithm. And magenta boxes on these images, I'll show you a set of images, are our hotspots from the MSAT system, and the black crosses are MODIS hotspots. I'm going to step from hour to hour. This is just the recalculated Australian data. There's no point going every 10 minutes. So at 0 UTC, there's only a few, this is from Terra, a few MODIS hotspots, whereas MSAT has hotspots because it's covering all of Australia. At 1 UTC, this is the MODIS Terra overpass, and it's picking up the hotspots in the Northern Territory, while MSAT is consistently getting them across the Australian region. 2 UTC, there's no MODIS observations. 3 UTC, none. At 4 UTC, this is the MODIS Aqua overpass. And when the MODIS Aqua overpass happens, we've got lots of black squares that happen in the region of our MSAT hotspots. So even though in the previous hours we had lots of MSAT hotspots and no MODIS accompaniment, doesn't necessarily mean that they weren't fires there. And this is 5 UTC, 6, 7 UTC, and 8 UTC. So you can get an idea of the kind of hotspots that we're detecting, but also the complexity of intercomparing our data with existing data sets, which don't exactly match what we're working with. And on this same day, what I'll show you is a little where we really dove in and calculated statistics to find out the accuracy of the MSAT system compared to the MODIS system. What you've got here is this, there's an Australian map at the top, there's a little box on the Australian map shows you the region that I've plotted. The region was a cutout that coincided with the MODIS overpass at a precise within a minute, where we had lots of hotspots. Left is without hotspots, so you can see the bright spots in the mid-infrared channel. On the right, you could see detections. Magenta squares indicate pixels where there was an MSAT and a MODIS hotspot within 1 pixel of each other. And this is then a 10-minute, like they're coincident in time and coincident in space. And the blue boxes show you MODIS hotspots where there was no accompanying MSAT hotspot. And the thing that we notice when we go through our data set is that we are going through and we're detecting the strongest Himawari-8 satellite hotspots. And we were deliberately conservative when we created the system because we didn't want to flood everybody with hotspots. So there are really weaker hotspots that are being detected by MODIS, but whether or not we'll be able to dive down to that with statistical reliability is still something that we need to look at, and there will be a limit beyond which we won't be able to connect. So when I looked at the real-time data that came out of the New South Wales Victoria trials starting 15th of March, that's when the algorithm became stable, and I looked all this way through to the 10th of January because that's just the data set I had at that time. And I had the MODIS data that was available at that time. I had archive quality data from March to September, and I had near real-time MODIS data from the 1st of October to the 10th of January. And there is a distinction between archive quality and near real-time for MODIS as well in quality. But using that data and comparing whenever MODIS had an overpass and there was hotspots in the overpass, we compared Himawari-8 data that was within 10 minutes and within that same region. And we looked for matches within plus or minus 1 pixel. And I can't, oh, there we go, I'm just moving the videos because I can't see my slide. From that, we found a 92% agreement. For every MSAT hotspot, there was a MODIS hotspot near that location within 1 pixel, coincident in time and coincident in space 92% of the time. When we reversed the question and we looked at every time there was a MODIS hotspot, was there a Himawari-8 hotspot within 1 pixel and within a 10-minute window? That happened 50% of the time. So 92% of the time for the MSAT hotspot algorithm is really good, actually. 92% of the time when we said there was a hotspot, MODIS agreed. You have to remember that there's differences between how we handle cloud and how MODIS handles cloud and how we handle data generally. And there will be times when the swath that we've created is not exactly accurate as well. So there's reasons why it's not exactly 100%, and maybe it won't be 100% because Himawari-8 might be viewing the data when a cloud's passed by as well. So there might be differences anyway. But this 49% in MODIS, I'm going to dive down and try and explain to you what's going on there as well. So hold on, move that back. So when you dive down and you look at the actual spectral characteristics of the hotspots when they've had a match or they haven't had a match, interesting things start to come out of the data. This is looking at the spectral qualities of the MSAT hotspots and whether they had a match or whether they were found or not found with a MODIS hotspot nearby. And the two data sets look quite similar. This is a mid-infrared on the right and the mid-infrared minus the thermal infrared on the left, and the mid-infrared minus the thermal infrared on the right. There's not much difference in the spectral characteristics between MSAT hotspots that had a match or MSAT hotspots that didn't have a match. But when we reverse that question and we look at the MODIS hotspots and we look at the spectral qualities of the MODIS hotspots and we separate the data into two data sets, ones that had an MSAT hotspot nearby and ones that didn't. Ones that did are in orange and ones that didn't are in blue. And you can see that there's spectral differences between these data sets. Generally for MODIS hotspots that also had an MSAT hotspot coincident in time and space, these are stronger ones with larger MIR values, and the difference between the MIR and thermal infrared was higher as well. And in contrast, that was not true of the ones that didn't have a match. They were generally lower, had lower MIR values and lower differences between their mid-infrared and thermal infrared values. And this is actually critically important. It comes back to what we were talking about before with the spatial detail that you get back from a geostationary satellite versus a low Earth orbiting satellite. Because the low Earth orbit satellite travels closer to the Earth, MODIS has a spatial resolution in the mid-infrared of roughly 1 kilometer by 1 kilometer per pixel. It changes depending on where you are in the swath, but in the center of the band, it's roughly 1 kilometer by 1 kilometer. So you can see the little box I'm showing on the lower right is my approximate, like showing you a pixel. A pixel gives you one value back. And inside that pixel, you can have a lot of complicated information going on. The blue dot shows the approximate height dividing up of a pixel into 4 when you compare a Himawari-8 pixel to a MODIS pixel. And when you take a little flyer and you put it in a MODIS pixel, which is like the size of a Himawari-8 pixel, it takes up a lot more of the room in a fractional sense compared to the Himawari-8 satellite. So for a MODIS satellite, you're going to get much higher brightness temperatures of fire than you would for Himawari-8 satellite. So a low MODIS middle infrared value or difference is unlikely to be detected in a Himawari-8 sense because it would be a factor of 4 times lower or something like that. So it's a complex comparison. So there's also, when I looked at the results, I was thinking to myself again, I was like, the problem with this space is we can give you hotspots, we can give you data, but when it comes to actually, you know, saying, and these are the results, and we know that we're right, and we're always right, there's actually no comparative data set to compare it to. There are other geostationary satellite algorithms, but they're generally being applied to places like America. And the ones that are looking at Himawari are fairly new as well, and they're not necessarily any more accurate. So you can think about it, we do the very strict coincident space and time comparison with MODIS, and we can consider relaxing the comparison and looking at, you know, what if Himawari-8 found that at a different time in the day? But then that opens a new set of problems, which is the fact that Himawari-8 does look at like Australia for fires all the other times of the day, and it's not fair to us in MODIS have a hotspot at a time when it wasn't passing over. Anyway, so it's complex. Anyway, we're looking at different ways to determine the objective accuracy of the Himawari-8 like our MSAT hotspot system. And one of the things that's been done here by one of our students that we're working with, it's called Simon Ramsey, is to compare all the Himawari-8 MSAT hotspots from November 2019, and he went and looked at the MODIS burn scar products. And what he found was that 98.21% of the time, if you compared a Himawari-8 hotspot, it fell into an area that MODIS burn scars had declared as burnt over the October to December period. So we're looking at new ways, and Corinne, you're free to jump in here if you want, to continue to objectively determine the quality of our hotspots. But you know, the challenges is that there's a lack of comparative data. Did you want to jump in, Corinne?
Yeah. So I guess essentially what we're trying to do with these evaluations of the accuracy of the hotspots is a number of things. So first of all, being able to document and report how well do the hotspots perform in terms of, say, false detections or a misdetection against other operational satellite products. So we're trying to do that with the low Earth orbiting satellites. We're trying to do that with other algorithms that have already been applied to Himawari-8, including WF-AVA. And so reporting a misclassification matrix and looking at those false detections and misdetections, and then drilling down as to try and understand why. But because as Shamel's mentioned, it's not really, because it's such a different set of data to what we have typically had access to, we need to explore and verify the data in numbers, like a number of ways. So we do the traditional intercomparison against other products. We start to look at something like saying, well, where has it burnt in the landscape according to our Himawari hotspots? and how does that compare to something independent like the Modus Burnt Area product, and what agreements do we see? And so in this example here, where we're looking at commission errors, but we can flip that question around and say, let's look at areas that Modus picked up as burnt, and did we have, you know, what was the agreement there in terms of Himawari hotspots that we delivered? As well as that, we can look at things like incident reporting, and again, looking at, say, persistence from our hotspots, again, compared to maps around fire severity. So we're really trying to take a multi-pronged approach in assessing these hotspots for their accuracy. And at the same time, keeping in mind, we've got this trade-off that we're trying to balance, which is that timeliness of getting the hotspots back into your hands. So also recording, you know, how long is it taking us for turnaround, the processing of the data and getting that out to the servers that you access for your operational systems. So yeah, so really a multi-pronged approach that we're doing with the verification and validation.
And
Thanks,
Corinne. Thanks, Corinne. So what I really want to kind of drive home from this presentation as well is that not only are we trying to create a new tool, this new tool is, you know, a new way of detecting fire hotspots from this Himawari data set, which is hugely exciting. In order to say how accurate it is, we actually have to also create new tools to say things about the accuracy of Himawari hotspots, because it's such a new space, which makes it complex but interesting. But we're going to finish up here and head over to our end users. So just to summarize what we've talked about is that satellite data can be used as a complementary data set to the other data sets that are full and rich that I know that you have, like your LiDAR data sets, things like that. But they are useful, but we need to be aware that there are different types of Earth observation satellites, and geostationary satellites are particularly useful in the weather and fire domain because of the high frequency and the fact that they can look at transient phenomena such as fire. At this point, I'm going to hand over to Naomi, and I'll stop sharing here.
Okay, I'll just share my screen. Share. Okay, so today I'm just going to talk about how we integrated Himawari-8 into our operational mapping system for Victoria over the 2019 fire season. So at the start of the season, in our operational mapping system in Victoria is called EMAP, and it's a shared system which CFA and DELP and all the other fire agencies use for operational response. We've had satellite hotspots from Modus available as a layer within EMAP for the last, I don't know, 4 or 5 years. And I think last summer we got the VIIRS hotspots integrated into our system. At the moment, the symbology which is on the screen is not reflective of the VIIRS hotspots, but it is showing the data. And so these are all feeds which are integrated automatically into the system, and the users can select either turning on the VIIRS hotspots or the Modus hotspots. So the difference between VIIRS and Modus obviously is the time interval and the scale. Modus was every 12 hours. This is just an example of the fires in East Gippsland, and just showing the hotspots, which are obviously, I think those hotspots are symbolised at about 12 hours. So that's just showing the fire activity within the landscape. And so they're providing additional information to our other near real-time information sources around fire extent. And so in this map, so the different types of near real-time data that we're using within EMAP is we get line scan data, which is coming from aircraft, that's integrated into our system so that the mapping officers can map the fire boundary. We get two types of line scan data depending on what planes are available. So we have the infrared bands and also multispectral bands. The infrared bands are great in that we also get day or night line scan information, while multispectral tend to be more limited to daylight. And so these bands can sense infrared radiation generated by the fires. And we also get AIG thermal imagery from helicopters. And that, once again, that's infrared bands. But you can see in this image that we had the fire extent for Gippsland and also for the northeast. And you can see some of New South Wales, and that there was huge areas of the state and across the border where we had no intel, and the hotspots are showing where the fire extent potentially is. So we had quite a few periods of time where we weren't getting any critical information, and so any other near real-time information. So hotspots became critical in providing that intelligence to the operational response around where potentially there was fire activity within the landscape that they didn't know about. And so this is around the 6th of January, this information. And you can see from this map and then the next map here that there's areas, I'm not sure if you can see my pointer, but certainly just east of Mount Buller and then the fire just across the border. It's very generalised, the fire extent. And so that's the mappers have actually mapped the fire shape around the hotspots that were available. So it's pretty rough and ready, but it was the only information we had coming in. The weather at that time, there was extremely thick smoke and a lot of cloud, so there was no aircraft getting up into the air to be able to fly for line scans. We weren't able to get any of the helicopters up for AIG to get any kind of near real-time information from those. There was no road access because all the roads were closed due to the fire activity, and even the smoke and the cloud were obscuring hotspots as well. So we weren't, at this point, we were only getting the MODIS and the VIIRS data. So that was 12 hourly or 3 hourly. So we weren't getting a lot of intel coming in. So we were operating blind in some ways. But on the 8th of January, we started talking to RMIT about getting the feed, and we talked to New South Wales RFS about getting the feed integrated into EMAP. And so, so this was just showing across the border where we use the hotspots to map the estimated boundary once again. But so around the 11th of January, we had the Himawari-8 feed actually integrated into our system. And so this is showing a much greater granularity. You can see there's fire activity up in New South Wales and in this area through the mountains, and also in East Gippsland. Just across the border, and in this area here, there's actually some hotspots. This data is from an early morning capture, and it's starting to show the information within 30-minute intervals, which is just such a game changer for our operational staff to start seeing where the actual activity is. The next slide is the 11th of January, and it's on in the evening, so it's quite late. It's around 11 p.m, but it's showing a lot of activity. So from the time periods, we've got a lot of hotspots in this area here, which are 2 to 4 or 4 to 6 hours old, which is fantastic that we're actually able to see this granularity and scale. We can see also areas where there's actual more recent fire activity within the last 2 hours, and obviously down near the border as well in this area here, as the fire was filling in where it hadn't burnt, there was activity in those as well. And also up in this fire here, you can see where the activity was. So it's starting to provide a lot of intel to our operational staff. So it showed fire activity within the fire boundary. So within the fire in New South Wales here, and also in this part of East Gippsland, you can see a lot of hotspots where the fire was active within the fire boundary that we had. And then there's also a whole lot of areas up here around the border here as well. You can see some areas where the fire was actually running. So the image was captured once again at 11 p.m. at night. And so there's active fire areas there, and there's also active fire areas here where it was filling in. So it allowed our operational staff to target their actual water bombing and their different activities once they're able to get back up into the air. And we found that the agreement between MODIS and Himawari-8 data was pretty good. Obviously the Himawari-8 data had a little bit more detail, but it was nice, the agreement. It gave the mapping officers and other operational staff who were looking at that data confidence to use it. And it also reflected quite nicely the fire boundaries as well, which obviously we want to see. And so here are just a few questions that I had to sort of throw to the group around how do we know about the accuracy of these hotspots after how many consistent records, say 10, 20, 30 minutes, 40 minutes. When do we call a record a valid record and it's not a false positive? Also, at what threshold does it become a valid record? And the last one is, obviously there's places on a hot day in summer, there'll be a lot of places within the landscape where there's like bare earth or rocky outcrops. How do you know it's a fire and not potentially a false positive? These are some of the things operationally, I suppose, we are interested in getting some information about, so that we know that when we're using this information, that we can say to our staff at a certain point, these records are definitely a fire, go out and send a crew to investigate, or so things like that. So there's some of the sort of thoughts I've sort of had around the data. So I'll just end my slideshow and I'll stop sharing. So
sorry. Hold on. Stop sharing. Sorry, I was just sharing my backup small PDF. All right, here I've got a movie of the 4th of January, which I prepared for Naomi today, and it's going to show you a bit of the complexity of the information that was available during that time period. So what you can see at the beginning, you got visible on the left and MIR on the right. It's a very fast movie. I'll play it a few times. I'm sorry, I didn't have time to slow it down. When it's incredibly smoky and cloudy during the visible part at the start of the movie, you could see a gap in the data, and that's due to our conservative formulation of the algorithm to begin with. But later in the day, the hotspots kick through and you get a real depth of information from the Himawari-8 dataset. And that's just raw data that came out of our system within about 2 minutes apart from the time when we had file system issues, which Stuart Matthews knows all about, out to the real fire services. Naomi, did you want to talk about the movie at all, or should we go on?
No,
like push on just because I'm just aware of time. So
okay, sure.
Yeah. Sorry, Naomi, to cut across you.
Fine.
And next we'll have Stuart.
Thanks, Shamel. So I'll talk a little bit about some of the work we did to support the research, and also how we started looking at and using the hotspot data operationally within the RFS. So we were involved in the project fairly on in the trial, and wanted to not just use the hotspots to look at operationally, but also to support Shamel and the team in doing evaluation as well. So our involvement sort of started at the end of the processing chain from RMIT, where they published the hotspots every 10 minutes through their FTP server. We grabbed that at the top left of the diagram and started archiving that along with the RFS public incident feed, which includes the location of incidents and their extent. So we've got a good record over the fire season of where we as an agency thought there were fires, and also where Himawari thought there were fires as well. Also then going down the left-hand side, publish those hotspot detections as a map feature layer onto one of our internal web pages, where they can be overlaid on our current incident feed and also on the current Himawari thermal band image. So if we go to the next slide. So this, back one. Sorry, Shamil, we go, yeah, okay, great. So this is just a screenshot of that website. So in here, we've got multiple data sources. So the underlying image is just the raw Himawari image, the most recently received one, which is grey and black for colder spots, yellow and red for hotter things that might be fires. And then over the top of that, we're able to overlay the hotspots as individual markers or clusters of markers. So the real advantage of doing that is it allows us to not just look at the current hotspots, but also to look back in time. So the individual Himawari images can be quite noisy, things can come and go. And also you can only look at what's happening now. So having that hotspot layer allowed us to look at, well, which things have been persisting here for longer, and also in the morning to look back at what was happening overnight. So the hotspot product allows us to do things we couldn't do just with the raw Himawari images, and couldn't do with MODIS either because of the large temporal gaps between images. And there's just some examples here. If you can see, there's an incident there on the left where there's a hotspot showing up in the RMIT data that's not in the same place as the incident marker. So it's been mapped in the wrong place, which has implications for notifying people about what that fire is doing, and also for trying to do predictions of that fire. You can also see on the right that there's a hotspot there that doesn't have an incident with it, which was later confirmed to be a permit burn that didn't have an incident associated with it. So that the satellite's picking up on things that are out there that at least some parts of the organisation weren't aware of. And we can also look at the relative activity of the fires in terms of not just the intensity of the heat signature in the current image, but also the accumulation of hotspots over time. So that combination of the raw imagery with all the detail that the hotspots provide gives us a lot more insight into what's happening out in the landscape. And that helps us with monitoring what fires are doing, but also is a good input into doing predictions, which is one of the core things for our team. So we might just go skip over that one, Shamel, and go to the last one, since we're almost out of time. And so it's just an example of where Himawari was really useful at a time when we didn't have other good operational intelligence, and similar to what Naomi talked about. So this was on the north coast of New South Wales, where a fire was reported at 8 o'clock in the evening, so we didn't have air ops going on. It was an area with not a lot of road access, not easy to move around, and so we weren't clear about where the fire was. But we knew that it was in amongst rural properties, and we needed to figure out where it was to be able to warn people if they were potentially threatened by that fire as it developed. So the satellite imagery was really useful there, along with the hotspots, to figure out where exactly was the fire. And you can see there that in some of those little inset images there, we've got the red called emergency warning area, and then the satellite pixels there showing that the fire was actually already outside of that, which helped us to get a prediction together quickly and warn people. And then the bottom left there is the line scan taken 10 o'clock the next morning. So it was that 14 hours between fire detection before we actually got some solid imagery of where it was. So having access to the Himawari imagery and the hotspots to monitor it overnight really helped with our situational awareness. So Yes, so we had really great experience using Himawari and hotspots for fire detection and monitoring, and the combination of the spatial mapping from the images along with the temporal availability of the hotspots has been a really great combination. Okay, thank you. That's all from me.
Thanks, Stuart. Now I'm going to hand over to Corinne.
Thanks, Jamel. If you want to go to that, we'll jump straight into it. One more, thanks. Yeah, I guess just to kind of wrap up a bit, it's, for us, the experience has really been, being in a bit of a sandpit to play with this new type of data, and then really get it out to the end users. So in a way, it's almost been a bit of a reverse process by implementing an algorithm and then doing the verification. So it's kind of, they've sort of happened in parallel. So the next steps for us is we're going to wrap up the live trial that we did with New South Wales, Victoria, to evaluate those different products. And part of that assessment will be looking at, can we kind of put some context around how sensitive can we actually make the algorithm to pick up lower intensity fires? Is there an FRP where we know we can't go below that without them, say, blowing out the false detections? So again, always that sensitive balance, keeping in mind it is a geostationary product. The next step is we're extending the algorithm to the whole of Australia, where we will conduct a repeat evaluation for the hotspots across all of the continent. So basically repeating the majority of what we're doing for New South Wales and Victoria for across the continent. The lessons that we learn from that in terms of improving the accuracy of the algorithm, we'll rebuild back into that algorithm. One of the steps that Shamel has already gone ahead of time, and which is great, she's translated the code to run in an AWS environment. What that means is it's now a scalable solution. So as Shamel mentioned earlier on in the presentation, we're hopefully able to now deliver hotspots across the continent in under a 2-minute window from the minute we acquire that data. So, being able to scale it now, it puts it into this architecture, this high performance computing environment that really allows us to really drill down to seconds of improving that delivery time, which I think in a fire detection context is obviously part of developing that solution. What we're aiming towards is being able to deliver a real-time live trial for the continent for this summer season. And because we've done so well with the AWS, we're probably ahead of time also in parallel handing over to a host agency to continue the product running into the future. Again, I'm aware of time, so I'm going to just jump straight ahead into saying, for those of you who are interested in being kept up to date with how the project's progressing, how we're going in terms of being able to deliver that continental-wide product, to send me an email. So I've popped my email down there for you. Just send me an email. I'll add you to a monthly, newsletter or an update, just to give you, a look into what are the things that we've been doing, what's been achieved, new products that are spinning out from what we've developed here. So we've been working on things around fire persistence or hotspot persistence in the landscape, and so we'll give you sort of screen grabs of some of those new developments. So if you're interested, just flick me an email and I'll pop you on the mailing list. So that's it from me. I think we hand back to you, Mike, I think, if you're around. Or Ben.
I'm here, I think.
Hi, Mike.
Okay, are there, I've got a few questions from the chat, but first are there any questions from the audience that aren't in the chat? I'll go through the chat ones in a minute. Silence is interesting. There was one question around smoke and dust, and I think Shamel did actually mention smoke in some of her comment, but essentially to smoke and dust obscure or complicate the signals?
They absolutely do. They do complicate the signals. But as I said, this algorithm was a first pass. We did the best that we could early and handed out the data early. And as we go back and like do our AWS trial and things like that, where we can really look through and start fine tuning the algorithm, we're going to concentrate effort to see what, if anything, we can do in those scenarios. And it does look hopeful, in my opinion.
There was another question around bare earth and hot rocks that currently show up in the Modus hotspots, and whether that's still a problem.
So it's a scientific issue, and it's kind of a scientific issue and a validation issue at the same time. We know the physics that should help us avoid those issues, but it's always a balance between trying to avoid that and then not miss out on real fires as well. So I would love feedback from the users actually of exact instances when they truly believe that the hotspot coincided with a hot rock, because that's someone that's not in the field. I'm not going to have that level of experience. That's a place where you can actually help. If you can tell us, then we can dig down into the data, and because we've got thousands of hotspots to look at, it's difficult to kind of drill down into ones that are of particular importance. But if you can tell us that this one, we know this one is always a hotspot, is always a rock. There's two options. If it's always a rock, you can delete it from the data set and ignore it. And the other thing is that we can then take that data and look back at the algorithm and see what we can apply in terms of physics to correct that. But we did attempt to not have hot rocks in the first pass algorithm.
There's another question around, well, what's your confidence around that you're detecting heat from the fire as opposed to heat from the convection column? So the hot air above the fire.
A satellite, like a satellite instrument, can detect heat. It's not going to distinguish whether it's finding heat from a fire, heat from the ground, heat from something. So when you look at the Modus algorithm, they call it fire and thermal anomalies. So we can't make a distinguish between like the source of the heat. So I wouldn't actually be able to answer that.
I wonder, and I'm not sure, but I wonder if there would be a way of, I mean, I don't understand the dynamics or the velocities at which these heat or these convection columns work, but maybe there's a way of incorporating that temporal component, looking at persistence and motion to help maybe isolate those things out. But again, I think this is where we're approaching this point in the program where we've delivered that first iteration of the algorithm, and then the next question for us is, or as a community, what's the next best thing for us to do? What's the next most important question that we should be addressing to improve this particular algorithm coupled with the Himawari satellite data? So I think that's, these are the kinds of questions that we as a community need to ask and prioritise. So, which doesn't answer your question, sorry, Anthony, but yeah.
And it's probably not that simple in that if you've got a convection column, you've also got a lot of fire on the ground. So and you're probably not going to have people there to validate it. So it's something that, yeah, as you said, needs some thought about how we can look at the pattern of hotspots occurring to filter out what's what. There's a question around how far are we away from being able to replace other land-based systems like fire towers, and I suspect that's a question for the sector, not for Karen. That'll be when we're confident enough about hotspots to not have to have other forms of validation.
Can I make a point there though? And I'm probably like the least qualified person to make it, but I think, so from the start of like the real thing that I wanted to say was like the tool set. When you think about all the tools that you have available, I think we have to be careful in terms of using Himawari, where we're not going to think that this is the new shiny tool and this tool can replace the other tools in the set. I think there's room and there's a need to have multiple sources of information to make comments about fire. And I'd be scared about deleting a fire tower because you have access to Himawari-8 data personally.
It's all about that sensitivity of at what point can that particular sensor make that detection? How low can it go? What is that sensitivity? And that's also driven by, you know, the landscape type it's in, the obscuration of the canopy. All of those things obviously play into it. So no one solution is going to fit every particular fire in every particular landscape. So yeah, I think, you know, you almost need this consortium of intelligence and you know, how we pull all of those things together, I think is also important. But yeah, I don't think one single tool is ever the right answer. But again, like Shamel, you know, I'm not an FBAN person. I don't know, but yeah, just from what we've seen in the data, it would make sense that, you know, different data sets will perform or be better suited to particular fires in particular landscapes.
And certainly at an obvious level, smoke and cloud still are a problem. So you will need other systems to operate during cloudy and very smoky conditions.
Yeah.
Now, Naomi, you had some questions at the end of your presentation. Do you want to put those to Cara?
Yep, I can do that for you. Just hold on. Share. There you go.
You could have told me Naomi had questions before the presentation.
We talked about this. These are the same questions.
Okay. How do we know they actually have inconsistent records? Before we call it not a false positive. So, and again, Shamel, you know, jump in when you think, you know, you have a different suggestion, and likewise, Stuart. Again, in terms of the accuracy and that consistency of records, which I'm going to call persistency, so that consistent reporting of that hotspot in the landscape or how it sort of connects to adjoining pixels, that's something we've started to explore and look at how we communicate that. As almost like whether that replaces the idea of hotspots or whether it's used as an ancillary product. I'm trying to think if I could quickly show something here, but we've started to play with sort of the visualization around not just looking at a single hotspot, but sort of growing that over time. So you have basically a depth of colour that shows how persistent that has been. So where it's darker, it's been much more, you know, on compared to, say, an adjacent pixel where it's much lighter in colour. So it's almost much more of a polygon description rather than these isolated points. In terms of these thresholds too, for a valid record, that's, you know, how to, and that's again something the end user community is able to inform as well. You know, what are the things that you guys look for in order to have confidence that that this is something that is reliable, you know, and articulating that into a set of decisions is something that we could then implement into the algorithm to help, I guess, create that solution that matches the expectations that the end user community have. I think one thing, Shamel, that we missed or we should also point out to is because of things like cloud, that if we don't get all the data that we need to give us that statistical reliability of data that we need to process to put out a hotspot or to calculate for hotspots, where that hasn't been met, we don't then calculate hotspots, but it doesn't necessarily mean there's no hotspot. So that's another level of complexity. And this is true for all satellite hotspot products, not just for Himawari, that if there's cloud, you're not going to have a hotspot detection, even though there may or may not be an actual fire underground, like not underground, under that cloud. So we need to think about whether there's any utility in creating, again, another ancillary product to go with the hotspots that says, well, it's basically a mask that says, this is where we had data to process, this is where we didn't, and where we didn't have data to process, we can't make any assessment about whether or not there was fire in the landscape. So, but as I said, this is also true for all the other satellite products.
Right, Corinne, just to complicate it, and like it's It's just a necessary level of detail. It's that we don't not provide fire information if there's not enough data. It's that we only detect the strongest fires. So this is a really strong fire, we will go ahead and we'll give it to you anyway. But it's because the aim of our work is to give useful information. So, you know, it's not useful to you if we say there's fire everywhere, and that means that we get every fire that there is in the continent, but we also get thousands of fires that aren't. So it's that balance.
And that was the criticism of WFABA initially, was that there were all these false detections, that the utility of that as a product was then compromised. So it's all about that sensitivity. It's all about us understanding that fitness for purpose and how we communicate that. But I guess, this is really a first product, and we're looking to the community to tell us, you know, what works well, what doesn't work well, what are the next most important questions that you have that we should be prioritising in the time that we have left on this program, that we can look at addressing or having a crack at. So.
And please stop me if you think if you're running out of time. But I just thought, while you were talking, I had like 2 comments I'd like to make about the questions from Naomi as well. Number one, like this, how do we know about the accuracy and how long before you call it not a false positive? I think I would love to throw that to Stuart, because he's had the longest time of experience playing with hotspots. And I feel in some way that's an experience question more than a scientific question. That's a choice for you as FPANs to decide, this is how I use the product. And I'd love to hear what Stuart has to say about that. And for the second 2 problems, I wanted to say that I know it's very boring and I know it's very laborsome, but I think that these 2 questions are going to be answered by the things like what we're doing with our intercomparison with MODIS, sort of, you know, coincident time and space. It is quite boring and it's not very particularly interesting to everybody, but it's what we need to do in order to be able to publish. But if MODIS has been detecting fires for years, if they say it's a valid record and we can intercompare our data sets and get it to the point where we agree on these things and we agree on whether it's hot or not, you could start asking yourself the different question, which is, do we trust the MODIS data set? What do we think about that? If you don't trust the MODIS data set, then maybe that's something we should know about before we go away and do our comparisons to it. But there are some things that we can do just with large data sets and intercomparisons that can answer those questions if you trust the other data sets. But I would love to hear from Stuart about how they felt about this, you know, experience of using the hotspots. Are there times that change their opinions of how to use it?
Thanks, Shamil. Yeah, and I guess my approach has been to think of the hotspots as one of, you know, multiple, you know, sources of intelligence we're using to understand where a fire is and what it's doing. So, for instance, if we know there's a fire out there because it's been called in, but we don't know where it is, then we can see a hotspot in roughly the right place, then that combination gives us confidence that yes, there is fire, because that's where the uncertainty with the satellite is it a false positive or not? But then we know we have really high confidence in the spatial accuracy of the satellite. So we can then look at, well, the satellite says the fire's here. You know, we can be very confident that it is in that location. So I think for something like fire, where there is uncertainty about most sources of intelligence and operating in areas where ground truthing can be difficult, I think it's important to put the different pieces of evidence together. I don't, and I guess I haven't thought about it from a record keeping point of view, that we necessarily, you know, look back over the hotspots record and use that to reconstruct, you know, fire history as a primary source. Although, you know, that does seem to work quite well for MODIS in tropical areas. So, but I guess potentially you could do that in future if you had a very high level of confidence in the accuracy of the product. But at the moment, I think it's most sensible to use it along with other evidence to understand what's happening. And I think the value there is, and that alludes to your comments about fire towers, it's not something that you necessarily want to use by itself, but in combination with other things, it tells you a lot more about what's going on. with the fire out in the landscape.
I definitely agree. Sorry.
It's an improvement in the sense that its timeliness is better than MODIS. Waiting 6 hours for the next round of satellite is pretty ordinary, and a cycle of in the tens of minutes is much better, and that certainly would be the experience of both Naomi and Stuart highlighted, that it gave intelligence at times when we had nothing else. So that's an improvement in itself. So I think that's the first spot, and certainly we had there's examples where it's picking up stuff that MODIS isn't. So that's the other thing that we need to look at in terms of his better intelligence that we can use immediately. And then there's a human still involved. We'll probably never get rid of the human, but smart people look at the data and actually work out which one they trust today, because I don't think it's a case of trusting it forever. It's what's best today given the circumstances.
Yep.
Are there any other questions? Oh, sorry, Stuart.
Sorry, I was going to say that the temporal coverage was really important over this last fire season. Those very large fires down on the Victoria-New South Wales border were active on a couple of nights until sort of 3 a.m. in the morning, and there were no line scanning or air observers at that time. So really the only way we had to watch those fires growing was through the satellites. Yes, that's a really important bit to take home, I think. Here's a tool that worked on improving what we had at the time.
Susan, just a comment on that one is the fire behaviour this season was very different to normal. It didn't really decrease overnight like it normally does. It was actually, there was a lot of activity throughout the night. So in that sense, yeah, the hotspots were really helpful.
Sorry, just one point about the algorithm, which I'd like to sort of just get the community to think about when they're using it, is the algorithm works by regions, and we know what the regions are. The regions are the IBRA regions, and you have your really in-depth knowledge about your own region. There is the potential going forward that, the algorithm will perform better in some regions and less better in some regions. The regions differ by size. They're different by the actual, biogeographical characteristics. And I think it will come down to the F-bands as well to get a familiarity with, I feel like I trust it most in these types of regions, in that regions, has slightly different characteristics. So I know from my, experience that the IBRA data set split it up like this, but I would prefer it to be like this. I think that kind of localized knowledge overlaid on top of the algorithm is going to help people actually use the data that we're pushing towards you.
And that's going to form part of the validation work that we're doing, where we stratify the hotspots into those different bioregions to be able to understand where we get that reliability and where that reliability drops away, and to be able to report that as on a state bioregional context.
That's really useful to know. Are there any other questions from people listening? Obviously not. You've stunned them with your science.
It's like giving a lecture.
I'd just like to thank Shamel and Karen for their time. This was meant to be scheduled about 6 months ago, and it's probably better that it's now because you've actually got more to present. But it's certainly a piece of work that lots of people are interested in. The potential for satellite detection to supplement our intelligence sources is huge. And so thank you for your work, and thank you for your time presenting under well, webinars are probably not an arduous circumstance, but your work in the last few months probably has been. And we'll close it shortly. There will be additional webinars in the F-band network series happening. There's another one should go out this week, but scheduled for, notice will go out next week, scheduled for the 8th of July, I think it is. So please join us again next time, and thank you for joining us today.